Hi everyone, we have a new unit, Unit 12, where we are going to talk about conjugated pi systems. And these are the molecules that have conjugated dienes, and we may later on look at extended pi systems called polyenes. But let me draw you a couple structures so we know what kind of molecules we'll be dealing with. This is the first video for this unit. So this is the introduction. Diene. If I have a 5-carbon diene, the way that I could put those two double bonds, right, 2 for di, ene for alkene, is I could draw it like this. Okay. Or maybe I could separate the double bonds even further apart. But there's another way to situate 2 double bonds in a 5-carbon chain, and that's side by side. And the way you draw that, one way to draw that would be this way. 1, 2, 3. You have an H, 4, 5. So a combination of Lewis structures and line structures. These have specific names or specific classifications. This is called a conjugated diene. You could recognize conjugated pi systems from the alternating pattern between double bonds and single bonds. You have double bond, single bond, double bond. They're alternating. Conjugated dienes have special stabilities, unique reactions compared to other types of dienes. This one, we could call it a isolated diene. You separate the two double bonds further apart. And this one has a special name. It's called cumulated diene. Or this is a class of molecules called the allenes. Okay. My question to you all is, can you assign the hybridization of every carbon in each of these 3 molecules? Okay. Let's start from the right this time. What's the hybridization of that carbon, this carbon, this carbon, and we'll do one of these carbons right here. Same thing for this. Hybridizations. We'll do all 5. Actually, let's do all 5 for all 3. Okay, go ahead and pause your video and write me SP, SP2, or SP3 for each of these arrows. Pause the video, come back when you've had some time to jot down your answers. Okay. We're going to start from the right, and this carbon here has 3. If you've learned hybridization from me, we call these balloons or areas of electron density. There's 3 of them. And 3 balloons, when you hold them from the ends, separate into trigonoplanar, and the hybridization is sp2. See that? Which is a little bit overexposed. This carbon is weird. Okay, it looks like if we had 2 oxygens, it would be carbon dioxide. You have 2 balloons only. Okay, you count a double bond as 1 balloon. You count a triple bond as 1 balloon. So you hold 2 balloons from the ends, they end up being linear, and that's sp, 180 degrees. This one again, we're back to trigonoplanar, sp2. This is sp3, and this is sp3. I'm going to use different colors because I want to highlight the sp2s. You'll see why in just a second. Okay, What about the isolated diene? For the isolated diene, we have sp2, sp2, okay, and then we have a break in the sp2 chain, and this is now sp3, this middle carbon. Realize that? sp3. And then we're back to sp2, sp2. Again, I haven't mentioned why this is important that we locate the sp2 carbons. I'll do that in just a bit. Conjugated diene. We'll take a look at this one. sp2, sp2, sp2 again, sp2. So even though there's alternating and we have a single bond here, we have 4 carbons in a row that are all sp2. And I'll circle all of them like this. And then at the very end, for that 5th carbon, we do have an sp3. Think about a pi bond. Just a normal pi bond. Go back to the lecture where we talked about hybridization. And we have 2 carbons here that are sp2 hybridized. sp2 means that your orbitals are made out of an s, a p, and a p. That's why it's called sp2. But you know that carbon atoms and atoms in the second row of the periodic table have 3 p orbitals, px, py, and pz. What that means is that there is an unhybridized p orbital. Remember how we drew the orbital cartoon? We have a carbon, okay? We'll focus on the carbon on the left. And I said it was trigonoplanar. We get that trigonoplanar shape due to the sp2 orbitals, and you have 3 of them. You can imagine that your hydrogens are right here and here. If you want to label the orbitals, let's label it sp2. All the blue ones are sp2. Your hydrogens are contributing an s orbital. Where's that unhybridized p orbital? Remember, the p orbitals are dumbbell shaped, and we have a p orbital that is perpendicular 90 degrees to the sp2 orbitals. Where did I get 90 degrees? I thought trigonoplanar was 120 degrees. 120 degrees is separating the balloons, the blue balloons. But that p orbital is straight up and down, perpendicular to these 3 balloons that are coming in and out of the plane and to the right. So it's perpendicular, the p orbital. You know that this is a pi bond, right? For this bond right here, you have a sigma bond and a pi bond. Well, what's making the pi bond? It's the p orbitals of the 2 carbons. So here's your sigma bond, an overlap of the sp2 orbitals. But also, as these carbons get closer, okay, this is not to scale. Your p orbitals should be a little bit wider, and the carbons should be much closer. You'd get an overlap right there. Think about where your electrons are now. You have 4 valence electrons for carbon. 1, 2, 3, and then the 4th one in the p orbital. 1, 2, 3, 4. Oh, no. See, we already have 1 electron in the p orbital. Let me count again. 1, 2, 3, and this one needs an electron because it's making a bond with hydrogen. And if you want to draw the hydrogen electron, you can. Those are your bonds to hydrogen. Can you imagine if there was another carbon next door that was also sp2? We already have sharing of electrons between these 2 p orbitals. But what if next door there was another carbon that's sp2 with its own p orbital? Wouldn't we have 3 p orbitals in a row? They would all be overlapping, and we would share the electrons between 3 carbons now. This is like resonance, okay? You've heard that delocalized electrons add to the stability. Look at that. Imagine that each of these carbons has that p orbital aligned, like we have here. If you want, draw it kind of on its side, like this. Okay? Think about your p orbitals. P here, P here, a P here, and a P here. Because I have 4 sp2 orbitals in a row, right here. Okay? Look at those. How many pi electrons do I have? I have 1, 2, 3, 4 pi electrons. Pi electrons are the electrons that are involved in pi bonds. Or the shortcut is the pi electrons are in the p orbitals. 1, 2, because we have 1 pi bond. But for the diene, we have 2 pi bonds. So there are 4 pi electrons. 1. It doesn't matter if you put the electron on the top lobe or bottom lobe. It doesn't matter. Okay, but here our conclusion is that we have 4 delocalized pi electrons. Now, am I going to show delocalization with resonance? You could, but really it's just a very loose containment of these 4 electrons that are going up and down the system, up and down the carbon chain. Not this carbon though, right? This carbon is sp3. This has no p orbital to accept an electron. So we have this sharing of electrons. That adds to the stability of conjugated dienes. So conjugated dienes are more stable due to the chain of sp2 carbons, which allows for the delocalization of the pi electrons. Is that true? Well, we're going to see an experiment, or describe an experiment in just a bit, that shows this. But let's take a look at the isolated diene. See, for the isolated diene, you have 2 p orbitals here sharing those 2 electrons. You have 2 p orbitals here sharing those 2 pi electrons. We have an interruption in the chain. So the 2 electrons here are isolated. They can't go to the other side of the molecule. Same thing with these 2 pi electrons, because there's no p orbital in the middle. This is different. Your pi electrons can be shared between 1, 2, 3, 4 carbons. These are not shared. They're, again, isolated, or you could say they are localized between these 2 carbons and these 2 carbons. Last one. Believe it or not, accumulated dienes are the least stable. Are the least stable. I'm not going to get into why they're the least stable, but I could tell you why there's no delocalization. Take a look. I made a couple of models of these 3 systems. Let me zoom out so you can see the full models. The conjugated diene looks like this. Okay. And think about it. Where are your p orbitals? I don't have the p orbitals on the model, but I do have the double bonds. But the p orbitals are, if you put this on its side, and you have a p lobe right, a p orbital right here, up and down, up and down, up and down, up and down. So you could have this molecule conjugated. Now, yes, if it twists out of the plane, then your p orbitals are not aligned. But in actuality, the molecule is most stable when they are aligned. And you have the molecule flat like this, and your p orbitals are now, if I hold the molecule like this, up and down. I'm not going to make a model. Look at the isolated. The isolated is here, and it doesn't matter if these p orbitals are aligned because they're too far apart. There's the p orbital on this carbon and this carbon. So yeah, you can, twist this as much as you want, and it's not that big of a deal in terms of the conformation stability. Okay, there's no really added benefit to have the molecule totally flat like this. But there is a benefit to have it flat for the conjugated diene. Got the D, conjugated. Accumulated, I told you that it was the least stable. And there's no delocalization. That's weird because I thought, well, what's going on here? Here is your accumulated diene. It looks like, let me put it upside down, like this. Double bonds right here. But do you notice how these two bonds, the hydrogen and the carbon, are perpendicular to these two hydrogens on the very end? Look at the double bonds. They're also perpendicular to each other. We don't get good alignment because in this orientation, imagine you have your two p orbitals here and here. Okay? But what about the p orbitals for making this bond? Those p orbitals are actually in and out of the plane, there and there. Right? You would have to tilt it, right, to get the p orbitals horizontal, vertical. Let me draw this for you. Okay? I mean, we did already a cartoon drawing for ethene and a cartoon drawing partially to show the p orbitals overlapping in a conjugated diene. This accumulated diene is odd because you have an sp carbon in the middle. What does that look like? So you have a carbon all the way to the left, and that carbon is sp2 hybridized. So you do have this p orbital. And yes, you're making a pi bond to the second molecule. It's true that you have your p orbitals, sp2 orbitals, right there, right there. Again, what are we drawing? We're drawing that molecule right there. But that middle carbon is not sp2 hybridized, it's just sp. What's sp? You have a linear orientation of your sp orbitals. What the heck? You have two p orbitals that are unhybridized. We already drew one straight up and down. The other one is sideways, in and out of the plane. So if you're trying to make a double bond between this middle carbon and the carbon to its right, what do you have to do? You have to twist that carbon so now its p orbital is in and out of the plane. So I know it's hard to see. Let me just finish the sp2. Oh, so this is even harder because now two sp2 orbitals are up and down. It's getting really kind of crazy. So let me draw you the dashed lines to show you where the p orbitals are and the pi bonds. So there's a one pi bond here between the two p orbitals that are straight up and down. But here we have two p orbitals that are on their side. Okay? It's hard to show on a flat piece of paper, but basically my pi bond for this first two carbons looks like this. But the pi bond between carbon 2 and 3 are actually like this. So you basically have a cross for the middle carbon. This is horrific. We have a cross for the middle carbon. See, there's your cross, two p orbitals. And we have one set to the right, alignment between the black and the green pen. And we have alignment between the blue and the red pen, but it's perpendicular. Perpendicular relative to the black and green pen. So what does that mean? Focus on the blue and red. You have two pi electrons being shared between those two. Now focus on the black and green. You have two pi electrons being shared between those two. But do you notice that there's actually no way for those electrons to jump into the blue-red system? And there's no way for the blue-red electrons to jump over to the black and green because there is no overlap. See, that's not an overlap because right in the middle is the atom carbon. So there is no overlap. There is no pathway to go from one pi bond to the next. Again, this is hard to visualize at first. There's some good pictures on the internet showing this, but basically, your pi electrons are still isolated from each other. There is no delocalization. Delocalization, okay, of the 4 pi electrons. I alluded to an experiment that sort of proves that we can predict stability based on whether something's conjugated or not conjugated. Get aligned here. So the bulk of the talk for the rest of this video and future videos, they're going to be on conjugated dienes, and maybe a little bit of isolated just to compare. We're basically done with cumulated dienes. We don't do any reactions typically on cumulated dienes. We don't usually try to make cumulated dienes either. And let me just draw one more picture though, and then we'll get off this cumulated diene or the alene part of this video. Let me draw you this. I think this picture may actually be even better. So those are your 3 carbons of an alene. It's a general class of molecules where you have the double bonds with a shared carbon between them. I think this would be much better. When you draw your hydrogens, you know that this carbon on the left has 2 hydrogens. The carbon on the right, actually those 2 hydrogens, if you recall, are perpendicular. That's unusual, right? Normally for the conjugated dienes, do you see how those hydrogens are all parallel to each other? Because we aligned the pi bonds and made the molecule flat. But let me show you alene. Let me make this real quick. Take a look at, if you take your models and you make this molecule, take a look at that. Isn't that interesting? My 2 hydrogens here are in the plane, but because of this sp carbon, and we need to align the p orbitals for this last carbon, it had to twist. And look at these 2 hydrogens now, one in the plane and one out of the plane. And I could rotate it, and you could tell that those hydrogens are perpendicular to each other. Or you could say the planes made by the 2 sides, they're perpendicular to each other. Perpendicular, okay, now still perpendicular. I don't get it. All right. That's all I want to say. Very interesting. Not chemistry, but geometries of cumulated dienes. All right. That experiment that I wanted to talk about. If I have, I'm going to try to fit it on this page. If I have an energy diagram, E, you understand that the higher up the graph, the more energetic, but also the less stable. Right? Stability means you're in the valley, right? If you're very at the tippy top of the hill, you're kind of unstable, and you'd rather just ski downward to the valley. So the valleys are more stable. If you take a isolated diene, one that we looked at the top of the page, okay? Let's say we have theoretically this energy, this height. When you do a reaction called hydrogenation, H2, you all know this, you get pentane. And heat is released. How much heat is released? It's exothermic. So the amount of heat released is around 250 kilojoules per mole. To me, what that means is that each double bond contributes 125 kilojoules per mole. 125, 125. Okay. That's how we're going to think about it. But if we have a conjugated diene, when we do the hydrogenation, we get the same pentane. We end up in the same spot. How much heat is released, though, when we hydrogenate a conjugated diene? The amount of heat we release when we hydrogenate a conjugated diene is going to be about, give me 1 second, let me figure this out, 226. Or we'll just round to 225. What does that mean? It ended up in the same place, but it released less energy. So do you think it's higher up the hill or lower on the hill? If it was higher up the hill, it would have released much more energy than 250. So it only released 225. It's actually lower on the hill. That's the stabilization due to conjugation. So the missing, right? The missing 25 kilojoules per mole it's due to conjugation. Conjugation lowering from the theoretical height down to its actual height. Okay. So there's something going on between these pi bonds when you get them close together and you make them conjugated. You're gaining 25 kilojoules per mole of stability. Okay. So this 25 kilojoules per mole due to conjugation stabilization. That does have a effect on the reactivity of these two molecules. Think about adding HBr, right? You could add HBr in two places here, and it would be, I gotta be very careful about this. The reaction will go faster, okay? Whereas these are conjugated, it has more stability, so it's actually a little bit less reactive. There are other consequences of this, which we'll get to the next video when we talk more about reactions. Let me just give you a kind of a preview. Something unique about a conjugated diene. We have this molecule here, and we do HBr. Remember what the first step of that is? You're going to use a double bond to grab an H, and you form a carbocation that's stable. Okay, Markovnikov talked about this, right? I like to say the rich get richer. So here's actually the carbon that has the most hydrogens in the pi system, 2 hydrogens. So that last carbon is going to get the hydrogen, which renders this carbon a carbocation. And then normally, right, if this was just one double bond, you would put the bromine right there, right where the carbocation is. What do you notice about this? Because the diene was conjugated, that double bond is perfectly situated to do this action right there, to do resonance. And we get a new carbocation. Now the molecule is symmetrical, so we would end up with the same product. But let's make it not symmetrical, okay? What this is showing you is that due to the conjugation, we could have the sharing of electrons even when it's a cation. And due to that sharing of electrons, we have now two possible intermediates to draw my alkyl halide. Okay? Or better yet, my allylic halide. Right? If you put the bromine here, wouldn't that be allylic? And if you put the bromine here, wouldn't that be allylic? I feel like we've seen this before. Definitely talked about allylic carbons and their stability. But anyway, in the next video, we're going to talk about this addition reaction. And we are going to get mixtures.